What if the next great earthquake doesn't begin with a violent jolt, but with a motion so slow you'll never feel it? Right now, beneath your home, your city, your feet, the earth may already be moving. Not suddenly, not dramatically, but silently. Millimeter by millimeter, day by day, year by year. We tend to imagine earthquakes as explosive moments, seconds of chaos that arrive without warning. But some of the most dangerous earthquakes on Earth are born in silence. They are the result of slow-motion fault movement, quietly accumulating stress for decades or even centuries. Today, we're uncovering Earth's silent quakes, the creeping fault lines that don't shake, don't roar, and don't warn us until it's too late. The Earth's crust is broken into massive tectonic plates, constantly in motion. Most move at about the speed your fingernails grow, just a few centimeters per year. When these plates suddenly slip, we feel earthquakes. But not all faults behave this way. Some faults move continuously, slowly, and smoothly. This process is known as aseismic creep. Unlike typical earthquakes, aseismic creep releases energy without producing strong seismic waves. There's no shaking, no immediate damage, just motion. At first glance, creep sounds harmless, almost comforting. If a fault is slipping slowly, doesn't that mean it's releasing stress safely? Not necessarily. In many cases, creep only occurs on parts of a fault. Other segments remain completely locked. The creeping sections can actually increase stress on the locked zones, stretching the geological rubber band tighter and tighter. And when those locked segments finally break, the result can be catastrophic. This isn't just a California story. Slow-moving faults exist beneath the Pacific Northwest, the Himalayas, the Andes, Japan, New Zealand, and parts of the Mediterranean. Some lie beneath megacities, others beneath oceans. Many are beneath regions unprepared for what's building below. So how do scientists detect motion that's slower than grass growing? The answer lies in some of the most precise measurement systems humans have ever built. One of the most powerful tools is INSAR, Interferometric Synthetic Aperture Radar. Satellites fire radar pulses toward Earth and measure how the reflected signal changes over time. By comparing images taken days, months, or years apart, scientists can detect ground movement as small as a few millimeters. These rainbow-colored maps reveal silent deformation patterns, showing entire regions slowly warping as faults creep beneath them. Thousands of high-precision GPS stations are also anchored into bedrock around the world. Unlike your phone's GPS, these systems track motion down to fractions of a millimeter. Together, INSAR and GPS have revealed something unsettling. Some of Earth's most dangerous faults are constantly moving, and we're only just beginning to understand what that means. On the ground, scientists install creep meters, instruments that directly measure fault movement across cracks in the Earth. Some have been recording data for over 50 years. Their records show steady motion, punctuated by strange episodes called slow slip events. These are periods where faults suddenly move faster than usual, but still without shaking. These slow slips can last days, weeks, or even months, and they often transfer stress to nearby locked fault segments. Which brings us to the question scientists are racing to answer. Are silent slips a warning sign or a countdown clock? Creeping faults don't just threaten future earthquakes, they cause damage right now. This continuous movement deforms the crust, building stress unevenly. Some areas stretch, while others compress. Over time, this invisible strain weakens rock, amplifies stress concentrations, and sets the stage for a sudden rupture. Slow slip can also trigger earthquake swarms, increased microseismic activity, and stress transfer to adjacent faults. In some cases, small creeping movements have been linked to the timing of larger earthquakes nearby. Even infrastructure is at risk. Pipelines slowly bend, bridges subtly shift, and buildings experience uneven foundation stress. Because the motion is gradual, damage often goes unnoticed until inspection reveals cracked supports, warped rails, or weakened joints. Silent motion leads to silent decay. Scientists studying past earthquakes increasingly find evidence that many were preceded by long-term creep or slow slip behavior. Sediment records, uplift patterns, and GPS reconstructions reveal years, or even decades, of silent deformation before a catastrophic rupture. One of the most alarming examples is the Cascadia subduction zone, stretching from Northern California to British Columbia. Here, The Huande-Fouquet Plate slowly dives beneath North America. This fault doesn't produce frequent large earthquakes, but it does experience recurring slow-slip events every 14 to 16 months. Each event redistributes stress along the fault. Geological evidence shows Cascadia is capable of producing magnitude 9 megathrust earthquakes, the last one occurring in the year 1700. The silence since then isn't reassuring, it's ominous. Other global hotspots include the San Andreas Fault, where creep in central California contrasts sharply with locked, dangerous segments near major cities. There's also the Himalayan frontal thrust, with its slow strain accumulation beneath one of the world's most densely populated regions. And let's not forget the Japan Trench, where slow slip played a role in stress evolution before the Tohoku earthquake in 2011. Across the globe, silent motion is shaping future disasters. Understanding silent quakes changes how we prepare. Creep data helps refine earthquake hazard maps, building codes, and long-term risk assessments. Cities built atop creeping faults must plan not only for sudden shaking, but for decades of silent deformation. Modern earthquake early warning systems don't predict quakes, but they can detect a rupture within seconds of it starting. Scientists are now exploring how slow-slip monitoring could improve long-term forecasting and risk models. We cannot stop tectonic motion, but we can build flexible infrastructure, enforce resilient design standards, and educate communities about these hidden risks. Preparedness isn't about fear, it's about awareness. The ground beneath us is never truly still. Some earthquakes shout their arrival. Others whisper for centuries. The silent quake is already happening beneath oceans, mountains, and cities alike. The question isn't if these slow-moving faults will release their stored energy, it's when, and whether we'll be ready when the silence finally breaks. I hope you have found this information on slow-moving quakes useful. Don't forget to like, share, and subscribe for more past, current, and future events in our world. Thanks for watching.